I'm Jakob Bludau. I'm currently a postdoc at Oak Ridge National Lab. I work 50% of my time roughly on Cocos, and the other half I work on various libraries that do particle simulations or other physics, but that also leverage Cocos basically. But today, this talk is going to be about, my slide deck went, oh, there it is. This talk is going to be about performance portable design patterns, so patterns that work in a performance portable context. And this is a part of BSSW. BSSW is an organization that tries to foster software sustainability. They give seminars, they have best practices, and they want to foster community engagement, but they also have fellowships. And I got awarded a fellowship for 2026, so I will have some chunk of my time for the next year. And the topic that I wanted to focus on is collecting these performance portable patterns and providing a means for the community to discuss them and educate and also just evolve them over time. So the main deliverable, because I think that's the best way to disseminate this knowledge, will be a website where everyone can basically discuss and where we also can evolve the patterns and find bugs and stuff like that. But first, we should define what do we mean by a design pattern. So it's a solution that you see that solves a very common problem that many people might have in different applications, and the design patterns basically formulates that and makes it reusable. And by doing that, it fundamentally facilitates code understanding. I don't know who here has read the book of the Gang of Four, the original one on design patterns. But if you have, and I tell you this and that is a factory, you immediately know what it does. If you even go so far as to name it my shiny new thing _ factory, you definitely know what you're going to find in that file. So these common concepts in the community really help for onboarding new members, for finding your way around a code base, for a ton of things. They also prevent mistakes that are commonly made, especially in performance portable programs. There is a myriad of rabbit holes that you could down to, but you don't want to, and you especially don't want to do a mistake and then later discover, oh, I should have spent more time on that. And by that, they fundamentally favor sustainable software design. So that means software designs that are maintainable and are working over a long time with changing developers in a dynamic environment. So design patterns are very, very powerful abstraction. Okay, now we know why this became the topic of my fellowship, but what is a design pattern? As already said, it's a reusable solution to a common problem, and is that in a form of a template. That doesn't mean like a C++ template, although it could be, but more like someone hands you a piece of paper where there is a rough sketch of what to do for a specific problem. And this can be adapted or should be adapted to your problem. You could, just like with a Gang of Four book, and you have a factory, and you look at that, you will have to adapt this to your problem, but then it still solves your problem. It's just a generic description of how to solve this. And since it gets adapted to your problem, it's also flexible with respect to specifics, like for example, which language are you using, which context are you using it in, or what content do you put inside the pattern. So if we look at it from a more hierarchical perspective, all our machines have restrictions. There are things you can do and things you can't do, and this becomes more and more apparent if you go to heterogeneous programming, and performance portable is even more restrictions that you will have. So you have some restrictions, and you hopefully have some basic elements already in your code that you try to reuse. Let's say you are doing matrix vector stuff. You probably have some basic elements like a vector already in some form or in some abstraction. But then you as a developer of an application, you have this large swath of code and design space that you need to cover, because you are the one that does compose the basic elements that are subject to these restrictions in order to achieve whatever you want to do. Let's say you do particle mechanics, you're gonna have to do a lot. And I said, hopefully for the basic elements, you can do them yourself, you can do all of that yourself, but you will waste your time. You probably, or you should, I will definitely give that recommendation, have a library that does some of these things for you. So where do design patterns live in that composition, basically, is they try to fill exactly this gap that you as an application developer just have the basic elements and have to still like a huge design space, and there's a ton of things that still can go wrong. And these patterns will help you as a application developer to more effectively leverage your basic elements and work around all the restrictions in your hardware. So that leads to the question, when should you go or reach for something that has design patterns inside? Well, if you're ever, or anything that you're ever gonna need is your basic element, let's say for Cocos you have a parallel 4, and all you're ever gonna do in your code is perfectly satisfied with one parallel 4, you're good, you don't need anything. But if your basic elements are no longer enough to basically get to a good solution and work around the restrictions that your hardware and your environment imposes on your code, then you should reach for that. Then, on the other hand, we could ask, okay, if they're already so close to these basic elements, why not just push them into a library? Because there is this delicate balance between upstreaming something into a library and therefore kind of fixing the interface and fixing how it works, and allowing for adaptability. If you keep it just as a pattern, you can just adapt it however you like. And that is basically why design patterns should not just be pushed into libraries, but should be something extra. But maybe let's make this a bit more feelable with an example. So let's first look at the text on the left side. So in performance portable programming, you have special restrictions. There are some people in this room that know them by heart. There are others that might not even have heard them, but there are a ton of restrictions. And the second thing is, if I give you a pattern and tell you, yeah, it's good for portable programming, it should do a clever thing. It should not just say, okay, I'm gonna send all my threads but one into a wait, and then I just do a serial. That's not a good pattern. But translating things from serial execution to efficient parallel code is pretty hard. And the code on the right side is an example. So let's say you have something like, I call it a generator that generates elements. And you can ask it, okay, how many elements do you generate for a certain index? And then it has a call operator that basically generates these elements. And before running, you don't know how many elements it's going to create for a certain index, because it might just be dependent on runtime information. Now let's say you want to store these elements in a vector in an ordered set. So you have your vector, and if you do it in serial, you would just for loop over your index range, so you start and iterate until you reach the end. And for every index, you ask a generator, well, how many elements do you want to add? And then you just push back. Now this will not work on the GPU because you cannot allocate while you're in a kernel. But you can still, with a pattern, get this to run in a parallel manner and not have to deal with this restriction. I called this pattern the generator processor scan pattern, because you have the generator, you will have something like a processor that processes the elements, and scan because the main element of why it works is a parallel scan, and then pattern because it's a pattern. Okay, but before we dive into the details, let's do some scoping. So what do we want? If whatever we push these elements into, in this case it was a vector, or like some data storage, already has enough memory to insert all of them, we only want to loop our index range once. Okay. If we use a parallel scan, we can do that because we can insert elements and count them at the same time. And then after the parallel scan exits, we definitely know how many elements we have, so we can, if necessary, reallocate and insert the rest. If not, if we already inserted all of them, we're done. But the challenge here is basically to track two indices, because we have one index that encompasses how many have we inserted and how many are like the total number of elements, and the other one is how many could we actually insert in this loop, where do we need to restart. In order to make it a bit easier to read, I added some colors. So all the indices that are related to the generator are going to be in green. All the indices related to the processor are going to be in blue. So okay, we start by you giving me a generator, you give me a processor, and you give me a range. I need to know which range I should iterate over. And the first thing I do is I do a parallel scan over the range. In every iteration, I ask the generator, hey, give me how many elements do you want to insert at a certain position. That's the number, the num in this block. And our parallel scan reserves the right to pass multiple times over something, and only if it's a final pass, you have a bifurcation and you can do something different. In this case, we use it if it's a final pass and our processor that needs to insert these elements has enough space, we go and insert them. If not, we don't. But what we do in any case is the last block, we do sum up the total. So we just add the number of elements a certain index wants to generate. So once the scan is passed, we have inserted all the elements we could, and we know the total number of elements that will ever be wanted to be processed, so we know how much space we're going to need. So after that, we can look at ourselves and look at the data and see, okay, do we have enough, or did we have enough storage? Could we insert all of them? If yes, we're done. If no, we ask the processor, please expand your storage, whatever it does behind the scenes, we don't care for now. We know how much it's going to be that in total will be inserted. And then we can restart from the index that was the last one that we were able to insert, so the last green index that we were able to insert. And with that, we can guarantee you that this will work in just 2 passes. And that is kind of beautiful and is something that might pop up in a ton of applications. But before we talk about the positive things, let's look at some things that we need to that need to be in place before we can even use this. So the first thing is your generator needs to be able to tell me how many elements do you want to insert per index. If it doesn't know that, then this is a way harder problem. They need to be countable. It also, that's an asterisk, if let's say you have 1 million things that want to, 1 million generator indices, and almost all of them don't do anything, and one wants to insert 10 million elements, this is not going to be the pattern for that. It's more like you have a set of particles and you want to know how many of them, for example, are in a boundary, something like that. So they either insert nothing or they insert roughly the same amount. Let's say everyone inserts like 0 to 5, then this pattern works. If you, as I said, one wants to insert 1 million, that will not be your best shot. The second thing is we are in parallel computing, so we basically run par and seq, so in parallel but non-sequential. So your generator and processor cannot basically have something that doesn't work in a non-sequential context. So you need to know as your generator, if I ask you for a certain index, you need to know that, and it cannot depend on all the indices before. But that's a general restriction of parallel programming. But if we have that, we get a bunch of guarantees. So with this pattern, because of the parallel scan, the processor will process the elements in their sequential index. That doesn't sound like much, but this basically guarantees you that the order of the elements will be like in the vector pushback loop that we started from in serial. They will have the same order, and that's a guarantee. And it could be the ordering just by index, that is fine, but you could add something in between and have your preferred order that you want. Let's say later down in your code, you want the memory access to be as coalesced as you can. That is one way to guarantee that. You get a guarantee on the order. The next thing you get is that every generator element, the element that the generator basically generates on the fly, will only be called once. If you think about this, it means that you can, for example, move stuff. Because you know no element will be generated twice and then discarded or something. You know it will only ever be generated once. The next thing we get as a guarantee, if the processor already has enough space, it will ever only be one pass, and we're done. And after the first pass, we always know how many indices or how many elements we will insert in total, and we will know the last index that actually was able to be inserted, and we can restart our second pass and only iterate over the rest of the range. And I mean, it's a small perk, but the range is completely independent, so you can say, okay, I want to start from 10 million and iterate to 10 million and 1. You don't need to start by 0. That's nice. All right, because it's HBSF, of course, we need to talk about performance. This is just a quick look at performance, but we see two graphs. The red one is for CPUs with OpenMP. The green one is for NVIDIA H100 with CUDA. Both of these were generated with Cocos, because that's just the easiest way for me to write these things. And you will see the speed up over the fraction of storage that your processor basically has. So we said if you have pre-allocated some memory and it is enough, that would be like you are pre-allocated fraction of 1. If you are at 0, you basically have no memory. The dashed line is the reference, and the reference is with respect to a, let's call it quote unquote naive implementation that does 3 loops over the whole index range. At first, it asks how many elements will every index want to insert. Then it does a scan and just computes the offsets, so it knows where to insert and the total number. Then it allocates, and then it goes with a parallel 4 and inserts all the elements. That's, by the way, the answer you get from, for example, if you ask any AI how to do this with thrust. You will get these 3 loops. And what we see is on CPU, so in the red graph, that for the worst case where we basically have nothing allocated and we need to do 2 passes in the pattern, we are a bit worse than the reference. But as soon as we have like 50% allocated, it's better. And if we have space for everything, if we already have enough memory space in our processor, we get a speed up of roughly 2. For the GPU, it looks a bit different. In the case of nothing pre-allocated, it actually is better than the reference implementation because it has less loops. In the case of 50% pre-allocated fraction, it is slower because we have more memory movement. But if you look at the scale, it is a few percent that it's slower. But if you already have enough memory pre-allocated in your processor, it will be faster by about 15%. So it's not the world, but it is something. And that's what I mean with like portable patterns. This works on CPU, GPU, it works on because it's implemented in Cocos. It works on any GPU that we support. Now this is my project just started, so this is a preliminary implementation, and we're currently working on trying this pattern, for example, in particle dynamics or in microstructure analysis and in geometric search, and seeing in these concrete HPC applications, how does it perform in terms of this speed up that you would get. And with that, the reason why I presented it here is these patterns are already out there. Most of us that work in HPC probably have had a problem similar to this before, probably have seen solutions, clever solutions, in some libraries, in some codes that they work with before. And I think it is very, very useful to the community of HPC and this whole performance portable programming as a whole if we go and try to collect them and curate them and give them a space where they live, where they're explained, where you can look them up, where you can, if you don't know how to solve your problem, you go there, you scroll through the things that are already there, and you hopefully get inspired, and you can hopefully off the shelf like say, okay, I'm gonna go take this one and this one and this one, and then this solves my problem. But we need to collect them first. So as said, I got some money and time from BSSW to look at this. So if you know a pattern that you think you have seen in your code, in code that you work with, that fits this description, it's solving a general problem, it could be used in different contexts with a little adaptation, just please let me know. You can either tag me and I will get a GitHub notification, or you can talk to me on Slack. I'm on the HPSF Slack. Or you can email me. You can probably even send a letter to ORNL with just my name on it, and it will get to me eventually. Just let me know, and I will do my best to first create a website to even host all of these and to collect them, and how to basically make them readable, make them easy to grasp, so you don't have to read like tons of pages before you can even tell if something helps you with your problem. And since this is it's actually a community project, and BSSW only focuses on community projects, if you want to contribute them yourself, please do so. I will do all I can to help you to make it fit my template or whatever. But if you say, okay, nice idea, but I don't have the time, still go, please tell me where to look, and I will do my best to extract the pattern from any open source code you point me to, where you think, and hopefully a line number, where you think there is a good pattern, please look at this, this could be beneficial. I will do my best and try to extract it and put it on the website. With that, there are some acknowledgements. Yeah, someone paid for it. This is the important thing. It's a community project. It will not work without your engagement. I think it will also help everyone in our context at HPSF or general HPC. And if you think about how much or how easy it is for you to reason about if someone tells you, oh, this is a factory pattern, or this is this and that pattern, and you immediately know what it does, we could get there for performance portable programming, but this will need the help of all of us. So, and with that, I hope you have questions, and I'm at the end of my talk. Yes.
So did you put much thoughts yet where you're going to host this thing? Like if people see some of the pattern that you have right now and they have some twist to it, what's the right place? to get the discussion started?
It's not finished yet, but it points to, the stars point to it being a GitHub IO website with basically its own repository behind it. So you can do issues, you can create discussions, you can run some CI if you want to. You can contribute code yourself. All of us are probably familiar with the workflow, so I guess that's the most common denominator of all of us. But I'm open to suggestions. If someone has a very good idea where to host it, sure. We get a red sign. Okay.
Thank you.
Sure.